In this video, you're going to learn how to differentiate the natural logarithm function f of x is ln of x, and we're going to differentiate this from first principles, and then we're going to use the result from this to differentiate the exponential function f of x equals e to the x, where you may recall that e is an irrational number. It's approximately equal to 2.718, and we call e the exponential constant. Now, before we can start to do the differentiation of the natural logarithm, we need a particular result concerning the exponential constant. So I'm going to derive that first. What I'd like you to do is I'd like you to think about this expression, 1 plus t all raised to the power 1 over t. And what we're going to do is we're going to evaluate this expression for different values of t and see what happens. I'm going to draw up a table of values. So I'm going to have two columns, t values, and then I'm going to evaluate 1 plus t to the power 1 over t. Now let's start with a very simple t value. Let's suppose t is 1. Let's work this out. When t is 1, this bracket becomes 1 plus 1, which is 2. And we want to raise it to the power 1 over t. And t is 1, so we're raising it to the power 1 over 1, which is still 1. And 2 to the power 1 is just 2. Let's pick a different value for t and see what happens. And this time I'm going to choose a smaller value for t. I'm going to let t be 0.01. Let's do the same thing. Put t in here. We'll get 1 plus 0.01, which is 1.01. And we're going to raise it to the power 1 divided by t, which is 0.01. And this is where you need a calculator. So I want 1.01 raised to the power 1 divided by 0.01. And that evaluates to 2.705. So we see, as t has been made smaller, the value of this expression, 1 plus t to the 1 over t, is increased from 2 to just over 2.7. Now let's see what happens when t gets even smaller. And this time, my value for t, I'm going to choose to be 0.3 noughts and a 1, 0.0001. And let's evaluate this expression again. So I want 1 plus t, which is going to be 1.0001, and I want to raise it to the power 1 over t, that's 1 over 0.0001. And again, we need a calculator for this. So in the calculator goes 1.0001. I'm going to raise it to the power 1 divided by 0.0001. And this time I get the value 2.718. Now this is an exercise that you could continue for yourself. It would be a very useful thing for you to do. And see what happens as t continues to get smaller and smaller and smaller, closer and closer to 0. And what we find is that as t gets smaller, this expression over here, 1 plus t to the power 1 over t, gets closer and closer and closer, surprise, surprise, to this value over here, 2.718, the exponential constant. Now that's a very important result that we'll need when we want to differentiate the natural logarithm of x from first principles. I want to formally write that down in a mathematical sort of way. What we've done is we've taken the expression 1 plus t raised to the power 1 over t, and we've evaluated this as t gets closer and closer to 0. And mathematically, we write this like this. We write lim for limit t tends to 0 of this expression is e, the exponential constant. In other words, the limit as t tends to 0 of 1 plus t raised to the power 1 over t is the exponential constant. And that is a key result that we'll need very soon. We're now ready to do a bit of differentiation from first principles. So I'm going to remind you a little bit about the formula for differentiation from first principles. What I'd like you to imagine is that we have a function, f of x, and what we're going to do is we're going to try to calculate the derivative of this function at a particular point here. Let's call the point we're interested in, let's call that point A. And A is the point with x-coordinate x. When we try to calculate the derivative of f of x at this point, that's when we try to calculate f dashed of x, what we're doing is calculating the gradient of the tangent to the curve at this point. So we're working out the gradient of the line which is just touching the curve at this point. Now, the way we do this mathematically is we move from our fixed point, A, to a nearby point a little bit further around the curve. Let's call this nearby point B. Now, the x-coordinate at B is just a little bit more than the x-coordinate at A. So the x-coordinate here is x plus a little bit more of x, and this little bit more of x in here we write as delta x. Delta x stands for a small change or small increment, as we call it, in x. So if this distance is delta x, the x-coordinate at B must be x plus delta x. What about the y-coordinates at A and B? Well, at A, the x-coordinate is x, and A lies on the graph of f of x. So the y-coordinate at A is just the function evaluated at x. So the y-coordinate at A is just f evaluated at x, or f of x. The y-coordinate at B, in a similar fashion, is just the function evaluated at this x value, which is x plus delta x. So the y-coordinate at B will be just the function evaluated at x plus delta x. Knowing all these values, f of x plus delta x, and x plus delta x, we can calculate the slope of the line through A and B. What's the slope of the line through A and B? Well, we do that by forming a little right-angled triangle in here, and then the slope of the line through A and B is this distance divided by this distance. Now, this distance is very straightforward to work out. It's the larger distance from the x-axis up to B, subtract the smaller distance from the x-axis up to A. In other words, this distance in here is f of x plus delta x minus f of x. This distance in here is just delta x. So now we're in a position to write down a formula for the slope of the line through A and B. We say that the slope of AB is equal to, it's this vertical distance, which we've got here, f of x plus delta x minus f of x, all divided by the horizontal distance, which is just delta x. What's this that we found here? This quantity is the slope of this line through A and B. What we're really interested in is the slope of the tangent at A. And we achieve that by bringing B closer and closer in to point A. What we do is we let B get closer and closer to A, and as that happens, the slope of this line will become eventually the slope of the tangent at A. Now, as we bring B round to A, what's happening is that delta x is getting closer and closer to 0. So what we want to do is we want to work out this expression in the limit as delta x approaches 0. So we want to work out the limit as delta x tends to 0 of all this. And when we work all that out, that will give us a value for the derivative of the function at point A. So that will define f dashed of x. That is a very important result that we'll need as well when we come to differentiate the natural logarithm from first principles. Now, I've rushed through this rather quickly. There's a whole unit on differentiation from first principles, and if you want a great deal more detail, I would go back and look at that video. Okay, we're now into the real business of the video. We want to learn how to differentiate this function. F of x is the natural logarithm ln of x. Now, to do that, we'll need lots of different things, lots of results from different branches of mathematics. So let's summarize what we'll need first. One thing we'll need is the formula for the derivative that we just wrote down. F dashed of x is the limit as delta x tends to 0 of f of x plus delta x minus f of x all over delta x. That's the formula for differentiation from first principles, and we'll apply that to this function in a minute. We'll also need the result that I gave you right at the beginning of the video, which was that the exponential constant e can be written as the limit as t tends to 0 of 1 plus t all raised to the power 1 over t. So that's another result that we'll need. We need a bit more, actually. We need something about logarithms. You need to know that the log of a minus the log of b is the log of a divided by b. That's one of the laws of logarithms. And another law of logarithms that we'll need is that if you have a multiple m times a logarithm, then that multiple can come inside as a power. So we can write m log a as the logarithm of a, bring it in as a power, to the power m. These are two laws of logarithms, and if you're not familiar with those, then you should go back and look at the unit on laws of logarithms. One final result, we need to know that the natural logarithm of the exponential constant e is 1. And again, you'll find information about that on the unit on logarithms. So all those things we'll need as we start to differentiate this function here. Okay, let's dive in. Here's our function. F of x is log x. We want to put this function log x into this formula for differentiation from first principles. To do that, we're going to have to evaluate f at x plus delta x. Let's do that. Now remember, this function, the logarithm, takes the log of the input. So when the input is x plus delta x, the output will be the logarithm of x plus delta x. So now we've got f of x plus delta x, and we've got f of x. We can plug them into the top line of the formula. F of x plus delta x minus f of x. What will that be? It'll be the logarithm of x plus delta x subtract f of x, so it'll be subtract the logarithm of x. We've a logarithm minus a logarithm. And this is where I'm going to use this law of logarithms here, which says that if you've got the log of a quantity minus the log of another quantity, that's the same as the log of the first term divided by the second term. So in other words, we can simplify these two logarithms to a single logarithm, the ln of x plus delta x, that's the first one, divided by the second one, which is just x. And because I know where this is going, I want to simplify this a little bit more. I'm going to recognise that within this bracket here, we've x divided by x, which is just 1, and we've delta x divided by x. Okay, so just a bit of tidying up there. Also, I'm keeping in mind that I've got this result here about the exponential constant. And in this limiting process here, you'll remember we have the quantity 1 plus t. In order that I can use this result, I'm going to make a substitution in here, and I'm going to write delta x over x as simply t, so that I can start to use this result. So I'm going to let delta x over x equal t. So I'll have a log of 1 plus t. We're still going to use the formula for differentiation from first principles. Let's go to that. We want f dashed of x is the limit of all this quantity. Let's take this quantity and divide it by delta x. So f of x plus delta x minus f of x divided by delta x. Well, the top line is this quantity in here, the logarithm. And we want to divide it all by delta x. But I've made a substitution here. I've let delta x over x equal t. In other words, delta x is x times t. So instead of the delta x here, I'm going to write this as 1 over x times t down there. Okay so far? So this is the expression for our derivative. The only thing we have to do is take the limit as delta x tends to 0. Let me write that expression down again. So that's where we'd got to. And what we want to do is let delta x tend to 0 now. Remember that delta x, we've said, was x times t. Remember also that x is a fixed point. We remember that from right back at the beginning when we came up with our formula for differentiation from first principles. The point A was a fixed point. It was B that was the variable point. So A was fixed, x was fixed. Now, if delta x tends to 0 and x is fixed, that means that t must tend to 0 as well. So in this process over here, we must let t tend to 0. So what we really want is the limit as t tends to 0 of 1 over xt natural logarithm of 1 plus t. And when we work this out, that's actually going to give us f dashed of x, the derivative that we're looking for. Now we're nearly finished. I just want to tidy this up a little bit more, take the limit, and then we'll be all done. You remember one of the laws of logarithms that I just wrote down was that m log a was log a to the power m. The power can be written outside, or a number outside can go inside as a power. Well, we've a 1 over t outside here, and that 1 over t I'm going to take inside the logarithm as a power. So I'm going to write this as the limit as t tends to 0 of 1 over x. I'm going to leave that bit outside, but the 1 over t bit will go inside and have logarithm 1 plus t, and 1 over t inside as a power will give me a 1 over t up there. Now this is looking much more like that result that we had at the very beginning. Remember the result we had at the beginning about the exponential constant? It said that e was the limit as t tends to 0 of 1 plus t to the power 1 over t. Now, you see I've got the 1 plus t to the 1 over t in here. I've got a limit as t tends to 0 there. The x is fixed. So what we can do is we can leave the 1 over x there. We want to take the limit as t tends to 0 of this expression in here, which is the logarithm of 1 plus t to the 1 over t. But we've already said that as t tends to 0, this quantity just tends to the exponential constant e. So we end up with just simply ln of e. Final result we had was that the natural logarithm of the exponential constant was 1. So this bit in here is going to simplify to just 1. In other words, we've deduced that the derivative f dashed of x is simply just 1 over x times 1, or 1 over x. That's a very important result. Let me summarize it for you. We're saying that if f of x is the natural logarithm of x, then f dashed of x, the derivative, is simply 1 over x. And we've proved that using differentiation from first principles. I'm well aware that to do that we require lots of different bits of mathematics from lots of different areas. Differentiation from first principles, properties of logarithms, and so on. So you may need to look back at lots of other bits of work that you've done in the past in order to pull all this together. But we've got a very important result now that we can use in lots of situations. What we've shown is that if you want to differentiate with respect to x the natural logarithm function, ln of x, the result that you'll get is 1 over x. We can use this result, whatever the letter is in here. So, for example, if we had d by dy of ln of y, the result will be 1 over y. If we had d by dt, ln of t, the result will be 1 over t. In other words, when you differentiate the natural logarithm function, you'll get 1 over whatever the variable is. Okay, very important result. We're going to use that result now to move on and differentiate the exponential function. So now I'm going to look at the function y is a function of x is equal to e to the x, or just simply y equals e to the x. And we're going to learn how to differentiate this exponential function. Let me remind you something about logarithms. If a equals b to the power c, an alternative way of writing this expression is that the logarithm to base b of a is c. This is something that's been discussed at great length in the unit on logarithms, but it's a result that we'll need here in order to differentiate the exponential function. What I want to do is take this y equals e to the power x and write it in its logarithmic form. And the logarithmic form, using the result over here, is that the log to base e of y is x. So that's just the logarithmic form of the same expression here. Now, log base e of x is what we call ln of x, the natural logarithm. And what I want to do is deal with this equivalent form instead of the original form. To differentiate this, what I want to do is differentiate both sides with respect to x. So I want d by dx of the left-hand side will equal d by dx of the right-hand side. Now this is easy. If you differentiate x with respect to x, you'll just get 1. The left-hand side needs a bit more thought. What we've got here is that y is a function of x, y is e to the x, and we're taking another function of it. We want the logarithm of y. So we've got a function of a function. We're trying to differentiate a function of a function. So we need a rule for differentiating functions of functions, and that's called a chain rule, or the rule for differentiating functions of a function. The rule says that if you want to differentiate this function of a function with respect to x, you differentiate it with respect to y, and then multiply by dy dx. So that's the function of a function rule applied there. And if you've not met that before, there's a unit on differentiating function of a function using the chain rule. On the right-hand side, we have 1. Nearly finished. All we have to do now is differentiate log y with respect to y. but we've just done a lot of that. We've just realised and proved that if you want to differentiate log y with respect to y, you'll just get 1 over y. So, following on from here, we'll get 1 over y multiplied by dy dx, and that's got to equal 1. So rearranging all this, dy dx will equal just y times 1, which is just y. But y is e to the x. So we've shown that dy dx is e to the x. So we have another very important result now, and the result is that if y is e to the power x, then the derivative dy dx is the same function, e to the power x. And that's a result which is well worth remembering. It will crop up over and over again in lots of different calculations, lots of different applications. In fact, the exponential function, or multiples of it, is the only function which, when you differentiate it, it gives you the same function that you started with. So that's something worth remembering.